Um, Good morning or afternoon, depending where you are. So today we are going to cover the last substantive lecture of the semester. The one after Thanksgiving would be mostly devoted to the paper helicopter. And so the method of manufactured solutions is this last topic. And it has to do with the fact that it's not difficult to find analytical solution in order to verify codes, but those typically restrict us to simple geometries, simple boundary conditions, and that means that the code will remain untested for the kind of problems that we want to solve. So first I want to ask you, when you consider the verification of a code, what are the considerations what criteria, if somebody gives you a code and you ask, how much can I trust it? What kind of tests you would expect the person who wrote the code to do? That is, if you try to formulate how you feel about the code, what would make you feel confident that you are going to use it and get good answers?
Comparative solutions for simple cases?
Well, comparative solutions for simple cases will not make you confident that it will do complicated cases. Yeah.
Compare with a complicated exam which we know the answers.
Yes, but the fact that it works for one example doesn't mean that it will work for another. So there is the need to compare, but there is one other requirement. So let me put the question in reverse, or let me tell you, there are a lot of complicated codes that people use today, like in my field of the analysis and design of aerospace structures, there is an Astran program that people do. For finite element analysis of more general structure, the most common program that we use is Abacus. Each one of them is a program or software that has hundreds of thousands, if not millions, lines of code. It's inconceivable that they don't have bugs in this code. It's really inconceivable. So still a lot of people use them and get good answers. So what do we expect? That is what makes those people, number one, trust those codes. Number two, have good reason to trust them because almost all the time they get good answers.
The models of the codes are based on our, the kinds of problems, the kinds of problems that we're dealing with.
Well, you said that the models of the code are based on what we need to do, so I'm not talking about the codes using the wrong models. They all use good models. I'm talking about simply verification, if you remember, is not the idea of choosing a good model. That's the field of validation where you compare it with reality. Verification is concerned whether the model was implemented correctly in the code. Yes?
I guess you just want to make sure that your model is a good extension of the laws that you're trying to, that your model hinges on, like the laws of physics or thermodynamics.
Well, you are saying that you want to make sure that your model is a reasonable manifestation of the physics, but that again will be tested by validation by comparing with physical tests. Here we are concerned with the simple case that somebody has taken all of these models, generated 2 million lines of code. Okay, that is, and we expect, you know, not everybody is as error prone as I am, but people are not perfect, and so we would expect that without verification, those 2 million lines of code will have thousands of errors. Even after verification, they may still have hundreds of errors. So what do we expect? So let me ask you the question in reverse. Why do you think those errors remain there?
No one has run into the consequence of those errors or detected them.
Okay, so this is a good answer, Ilan, that is, the errors are still there because nobody has stumbled across them. That is, there are two possibilities. One is that the errors have been exercised, but they are small, so that a person running them got an answer which is 1% different. Remember, I gave you an example where I used anti-optimization to expose an error in a code, where I got 1/3 of 1% difference. And that error has been there for several years before I stumbled across it. And the reason that it stayed there in spite of the person who wrote the code did extensive verification. But because this error usually led to small inaccuracies, it's stayed there. So the bottom line, what I'm trying to get you to tell me is that when we verify and there is an error in the code, how big the error will be will depend on the test case. And if you do a small number of tests, it could be that you'll never stumble on a case where the errors will be larger than the uncertainty that you have because of discretization error, because of round-off error, because of all the things that, or it will be larger, like my 1/3 of 1%, but you will lack confidence to report it and bug somebody about it. That is, I was in the unusual position that I knew very well the theory, and so I looked at 1/3 of 1% and I said, it couldn't be there. You know, in most situations, people that encounter 1/3 of 1% difference between the code will say, to practical purpose, this is verified. So the point is that verification against the set of solutions that we can get from analytical solutions is usually much less than we need to verify a code. That is, we want to run it for complicated cases, and we want to know whether the solution is right. And this is where the method of manufactured solution helps us. So let's take a simple example. The textbook has a more complicated example that I'm going to come later, but I picked this beam example, number one, because I teach beam equations in several courses, and also this is something that you get quite often, so I'm assuming that at least half of the students in the class have come across this equation, but even if you didn't, you can just look at it as a fourth order differential equation and take it at that. So we have this very simple differential equation, and if you take a class like mechanics of materials, there is a chance that you will have seen solution to this differential equation when you have a beam which doesn't change its cross section. So, well, let's use this chalk. A cantilever beam under an end load is a problem that people do a lot, or under distributed load. Or you see other kind of boundary conditions, like it's called simple support boundary conditions, where you So we have a lot of analytical solutions for the case that the beam stiffness is constant. So for those of you who are not familiar with this equation, E is Young modulus, and I is the beam moment of inertia. And if you have a typical 2x4 beam that you see in a house, it has a constant cross-section that is, it doesn't change, and you can solve this differential equation. The loading Q of x could be its own weight, or you can have some delta functions where you have concentrated loads applied to the beam. In either case, there are plenty of analytical solutions. But in many cases, it would be good to have a code that will solve it for us for a beam which doesn't have a constant cross-section. Could anybody give me an example where we may want to have something like that for wind loading, for example?
Well, like the base of a wind turbine, you may want to have decreasing cross-section as it goes up.
Okay, so a blade of a wind turbine is one example. The one that I have in mind is a skyscraper. If you think about a skyscraper, it's essentially a beam cantilever to the ground that in windy towns, I used to live in Chicago, you can estimate how much it's going to sway, and occasionally that caused the windows to pop out. In due to wind loading. So that would be something that people will use elaborate finite element model to analyze today, but if you just want to get a good approximation, you may want to program the solution of this equation, and that will give you an estimate instead of having to prepare a lot of data and wait a few hours to get something back. This is something that you'll get almost instantaneously. And so what would we use to verify that? So this is just an example. So I'm hearing myself talking in the background. Let's see if I can. Okay. So I didn't pick, I decided that the way a skyscraper tapers may be captured typically by cosine of x over L, where x goes from 0 to L. Anybody can tell me what's the value of cosine of 1, approximately? Not 1 degree, 1 radian. 1 radian is 57 degrees. I'm hoping that some of you know what's the cosine of 60 degrees. I'm sorry? 0.5. So we are considering here a beam that loses about 50% of its rigidity from top to bottom. So solving this differential equation may be either impossible or difficult or time-consuming. You know, these days with symbolic manipulation, it could be that it's not going to be too bad. But the idea of the method of manufactured solution is that we manufacture a solution instead of finding it. And so we can say, what's the wind loading on this skyscraper that would make it sway like W is equal to x squared? And so we plug in, if W is equal to x squared, d squared W dx squared is going to be 2. And then the second derivative of 2 cosine x over L is going to be minus 2 over L squared cosine of x over L. So that basically tells us if we will apply this wind loading, it's of course the wrong model for wind loading. Could anybody tell me why this is an unrealistic wind loading?
I think one assumption is you are solving it in one dimension.
I'm sorry?
You are solving it in one-dimensional case.
Yeah, I mean, this is a one-dimensional model of the building, so I have to apply one-dimensional wind loading, but you see, this is wind loading that would be maximum on the ground and then reduced to about half at the top, while we expect the wind to go in the other direction. So but it's complicated enough so that if our code will give us, for this kind of wind loading, a solution of W is equal to x squared, we will have substantial more confidence in the code than if we tested it only for constant cross-section beam. It basically will say, yeah, we have a test, and of course, we don't have to take d squared W dx squared equal to x squared. We can use the same method. Maybe we'll say d squared, let's say W is equal to some sign of x over L, and that will, or sine square, in order to satisfy the boundary condition and get a more complicated solution. So this is the method of manufactured solution. And what I'm going to do now is I'm going to try to see, well, actually, let's go over the procedure first, and then I'm going to have a top hat question. So this is the the first 4 steps in this general procedure is what Oberkamp and Roy say is the recipe. So you go and look at the mathematical model that underlies your code, and you write it as L of u equal to 0. And L is the differential operator, and u is the dependent variable. Then you choose an analytical form of the manufactured solution. I'm not sure that it has to be analytic, but that's what I did in the example. And then you apply the mathematical model L into the manufactured solution and obtain an analytical source term. Because Oberkamp and Roy are mostly coming from fluid mechanics and heat transfer, they talk about source terms. And that's what happens in 2-dimensional problems involving heat transfer or fluid mechanics. The right-hand side is some either fluid or thermal sources. In the case of solid mechanics, those would be like body forces or surface forces. And then you obtain the modified model by including the analytical source term S. That is, you're basically saying, I'll be solving now L of u equal to S. And I added the next step. If you apply S to your code, will you get that manufactured u? Now, the reason that I hedged about step 2 is that one of the things that you can do, like when I compared two codes, I can take essentially the displacements that I get from one code and plug them, and I say this is my manufactured solution, and see what kind of loading it generates on the other code, and compare the loading that I put on the original code to the loading that come out from the second one. So there are variations that you can play. So now here is, let me give you an example that doesn't have any differential equation. That is, you wrote a code to solve cosine x plus 7, the tangent of ln of x equal to a. And maybe Kelvin and Anirban here know that they have grappled recently with just solving algebraic equations, and writing a code that will do that is not always straightforward. And you want this equation solved for any a. So you wrote, how long was your MATLAB code for solving for the definition of the contour that will have the right center of pressure, Anirban? Do you?
I usually started with around 500 to 1,000. I think around 1,000 lines, but over the period of time, I could decrease it to close to 100 lines.
100 lines. Okay, so you write a MATLAB code to solve a complicated algebraic equation, and you want to verify it. So here is the equation, and I'm asking you, if you think about the spirit of manufactured solution, what value of A will you choose in order to verify that? So let me put top hat on. Yeah. And let me give you a hint. I already told you what that number is. And I put in some margin that is the answer. Taphard will accept as correct answer as long as you are within about 25%. So remember that what I'm asking you, what manufactured solution you'll have, which is what value of x will you invent in order to check this. I'm sorry?
I divided it into modules, so the final code is around
500. Okay. I mean, the point that I was trying to make is even to solve an algebraic equation, you oftentimes need to write a code that needs verification. Okay, I guess I'm not sure that mulling over it will take a long time, so I'll give you another half a minute. Okay. Okay, so actually there is probably, the answer that I was shooting for is 0.54. And let me explain, and then I'll welcome you explaining to me why you picked up some other numbers. So if I wanted to have a solution that I can check on the spot, that is without going and making complicated calculation, it makes sense to choose x equal to 1, because the log of x, the log of 1 is equal to 0, and the tangent of 0 is 0, in which case a would be the cosine of 1, which we have established a few minutes ago is close to 0.5. Actually, it's 0.54. So if you choose a as 0.54, you expect to get a solution x equal to 1, and that will verify the code. Anybody cares to explain how they chose some other number? So of course, if you are not in a setting where you need to choose one on the spot, you know, any x value that you will choose, you can calculate the a and verify the code. But if you, the reason that I picked 1 is that I'm often in situation where people present to me results like x as a function of a, you know, show me a graph, and I say, okay, I cannot calculate in my head for any other values, but for x equal to 1, I can immediately take a look at the result and verify it. So I'm doing the same kind of verification that you encounter in real life. That is, you will find yourself, whether you are professors or not professors, you'll find yourself in presentations where people will be presenting results of solution that they obtained, and sometimes those are your co-workers, and sometimes they are people who are trying to sell you something. And you are in the same position. You want to verify that what they are presenting is good, and so it's important to try and find essentially solutions for which you know the answer, and that's one way of doing it. Any questions? So the spirit of manufactured solution is to avoid the heavy work, that is applying the right-hand side of the boundary condition and getting a solution is a lot of work. Inventing a solution and finding what the loads that you or sources that you need to apply is much easier. Okay, so here are the remarks that Roy and Oberkampf give us, that manufactured solutions do not need to be physically realistic. And I gave that example to you with the wind loading. I picked up wind loading that were not physically realistic, but occasionally, if you are not careful, you are going to trip the code that makes an assumption, and they give the example of the dependence of, if I remember right, the speed of sound on the temperature, and where you will get the root of the temperature, and if your solution came up with a negative temperature, you will crash the code. The second thing relates to what we discussed previously, that you can have a lot of errors remain in the code if they produce errors that are small enough not to be noticed, or to be noticed and people that's shrugging it off. I don't have the time to look into why this is 0.5% away. And so if you are verifying a code with manufactured solutions that are dominated by one part of the differential operator, those of you who do fluid mechanics know that there are terms that come from turbulence, terms that come from inertia. And so you should be careful not to have manufactured solutions where some of the terms are too small. They recommend the use of trigonometric and exponential solution functions because they are infinitely differentiable. But I'm not sold on that because that can leave errors in the code that manifest themselves only when you have some discontinuities. And that last part is important. If you have a manufactured solution that varies gently, you will be able to verify it with a fairly coarse mesh. And that's important because, as I tried to show you last time, getting a complicated solution to converge may stretch your computational resources beyond what you can achieve. So now let's look at the textbook example. And this textbook example is more ambitious than I've been with the beam example. In the beam example, I just wanted to check that the code gives me the right answer. When you have discretized code, you also want to make sure that the algorithm that you applied is applied correctly so that the order of convergence that you believe you programmed in is achieved. Could anybody tell me why? So for example, in the Euler integration that we discussed last time, I told you that we can figure out that the discretization error varies linearly with the mesh. And here we will have an example where it was deduced from the algorithm that was used for the discretization that the order of convergence is 2. That means you have the mesh, the error reduces by a factor of 4. Why would we want to verify that? If the code gives us the right answer, what do we care whether the order of convergence is what the theory tells us it should be?
Because you don't want to run always with the finest mesh, so you need to do a convergence test. Say you want to get it to 95% accurate. You want to know that it's 95% accurate based on 2 tests.
So one thing that Ilan said is that if you know the order of convergence, you can extrapolate more effectively. And the other thing is a bit more basic. It's very rare that your mistakes will make the order of convergence higher than you planned on, they usually make it lower, which means that you will have to use a finer mesh to achieve the same accuracy, and that will simply cost you computer money or unhappy customers. What will happen if you verified the convergence rate and it was higher than the theory told you? That happens, by the way, from time to time.
Maybe that would happen in very specific scenarios.
Well, let me give you an example. I didn't run into more than one or two in my career, but one example was that in finite element analysis, people have used Gauss integration in order to calculate stiffness matrix, and then they noticed that the order of convergence of the stresses at those Gauss points was better than expected, and somebody worked very hard to show that it should happen. That is, you stumble across a way of wringing more accuracy from your code than you thought possible, so you go and prove that that's the way it should be. And what people do now is that they take advantage of that. Okay, so let's look at the example. The example that is given in the textbook is of the steady state heat conduction, where, to make it simple, you set the conduction coefficient in the x and y direction to be constant and equal to 1, so that the differential equation is partial square t, partial x squared plus partial square t, partial y squared is equal to s. Could anybody tell me which famous person is this differential equation linked to? I'm sorry?
Is Laplace?
If it's 0, it's Laplace. Fourier is the guy who invented the physics that leads to this equation if you put in the right conduction coefficient. But the equation that applies in many other fields, Poisson. So this is the Poisson equation. The reason that I'm bringing it up is all of those names is, number one, I believe that the people who teach us history in school don't know much about science, so they leave all the important people out and tell us about generals and kings instead of the really important people like Laplace and Poisson. And the other reason is that it gives you an idea of how old this equation is. So this is the model, the physical model, and then somebody invested quite a bit of time to derive a discrete algorithm for solving this equation, where he could prove that the discretization algorithm would have convergence of order 2, and then to check this code, this was the manufactured solution that was generated, including cosine only in the x direction, sine only in the y direction, and then sine of xy that changes all. And this is the way the solution looks. And what I'm asking you is what is needed to generate the manufactured solution beside the source term. That is, if we take the code and want the computer code to generate this solution, we can plug it into the differential equation and calculate the sum of the two second derivative and calculate S, which would be what we'll have to apply in terms of temperature flux applied at different points. What else would we need to do? We need to apply boundary conditions. So we basically have to calculate the temperature on the four boundaries and apply this temperature there. So this is that, and this was done with 5 grids ranging 9 by 9 to 129 to 129. And you see here the 33 by 33 grid that shows you that based on the solution, the grid was created so that it will capture where the gradients are largest. Could anybody tell me why those strange numbers? Yeah, that is, this is the number of nodes. So the number of cells is going to be 1 minus that. So 8 by 8, 16 by 16, and so on. And these are grids that don't change the boundary line. They just divide. When you go from 9 by 9 to 17 by 17, you simply take each cell and divide it by 2 in the x direction and by 2 in the y direction. And so on the right side, you have the first order of accuracy. Because you know the error, since you know the right answer, you can calculate from each pairs of grids what's the order of accuracy, and you can see that it starts from a little over 2 and converges to 2, and you have only 4 points because we have 5 grids and we use pairs. And on the left side, you have the L2 norm, and the dashed line shows you an exact quadratic slope, what it would look in this log scale. So indeed, we look at that and we say, yeah, we verified that for this manufactured solution, the code has second order convergence. Yes?
What's the L2 norm?
L2 norm is when you compare the solution of the code to the exact solution with the 9 by 9, you'll have 81 points that you need to compare to another set of 81 points. So you look at them as vectors of 81, and the difference is the vector of residuals or errors, and you take the L2 norms, which is the Euclidean length. That is the second norm. L1 norm would be simply the average, the sum of the absolute errors, and the L2 is the sum of the square and then square root, and so on. Other questions? Yes.
Why do we use bias grid instead of uniform grid? I think that bias is affects the tendency of error.
Yeah, I think that they did that because of the fact that the solution algorithms actually selected the grid, not only the way to solve it. It's not very clear from the textbook, but that was understanding that there was an initial stretching of the solution involved, and only after that the mesh was done. So it's, and to tell you the truth, when I'm looking at the sine and cosine terms, I don't exactly see that the largest gradients in the y direction, it makes sense, but in the x direction, like cosine of pi x over 15, the biggest derivative will be at x equal to pi over 2, which correspond to x equal to 7 rather than x equal to 3. So I'm not even sure whether there isn't a small mistake there, but that doesn't change the methodology. Other questions? Okay, that will be all.